All right, welcome to day 22.
You know, we often think the goal in machine learning is to build one single massive complex model that gets everything right. But what if that's not actually the best approach? What if a team of simple models could consistently outperform a lone genius? By the end of this, you'll understand how some of the most powerful algorithms out there are built not by being perfect, but by being really good at learning from their own mistakes.
Okay, so let's dive into the core idea. Imagine you train a simple decision tree to predict house prices. It's probably going to be decent, but it's definitely not going to be perfect. No single simple model ever is. It's going to make mistakes, it's going to have blind spots, and that's not a failure, it's an opportunity.
So let's look at the mistakes our first model makes. For one house, the actual price was $300K, but our model predicted $280K. That's an error of plus $20K. For another one, the actual price was $500K, but the model guessed $510K, so an error of minus $10K. This error column, which is technically called the residual, is basically a perfect logbook of everything our first model got wrong.
And this right here, this is the central idea of boosting. We're going to train a second model. But, and this is the key part, this second model isn't trying to predict house prices at all. Its only job is to predict that error column from the first model. It becomes a specialist, dedicated to figuring out the mistakes its predecessor made.
So how does this actually help us get a better prediction? Well, it's a team effort. We simply add the predictions together. Our first model says 280K. Then our second model, the mistake specialist, comes in and adds its correction, let's say plus 19K. The new team prediction is now 299K. Wow, that's a whole lot closer to the actual price of 300K.
And we don't just stop there. This process is a loop. We take the combined prediction of our current team, calculate the new, smaller errors, and then train a third model to correct those. Each new model we add to the team focuses on the remaining, more difficult mistakes, making the entire group progressively stronger.
So, this idea of fitting a new model to the errors, that's the basic intuition. But to make this a truly general and powerful technique, we need to introduce the concept that gives gradient boosting its name.
So far, we've only talked about correcting simple numerical errors. But what if your model is trying to classify an image? The real magic of gradient boosting is that it generalizes this idea. Instead of residuals, it uses something called pseudo-residuals. Just think of these as a more sophisticated way to measure a model's mistakes for any kind of task. They're calculated as the negative gradient of the loss function, and that's really just a powerful math trick that gives us a universal recipe for figuring out which direction our model is wrong so the next model knows exactly what to fix. Now, this powerful concept was implemented and optimized in a library that pretty much took the machine learning world by storm, XGBoost, which stands for Extreme Gradient Boosting. So what makes it smarter? Well, XGBoost isn't just focused on reducing error. It also adds a penalty for model complexity right into its objective function. This means if two different trees reduce the error by a similar amount, XGBoost will always choose the simpler one. This is a form of regularization, and it's absolutely critical for preventing overfitting, making sure the model works well on new data it's never seen before.
And what makes it so extremely fast? Well, just brilliant systems engineering. Things like sparsity-aware split finding let it handle messy, real-world data with missing values automatically. Column block for parallel learning organizes the data perfectly so it can use all the cores on a modern processor at once. And for truly massive data sets that don't even fit in memory, out-of-core computation lets it work on the problem in chunks. It's just built for speed at scale.
Let's just focus on that sparsity awareness for a second. Real-world data is rarely perfect. It almost always has missing values. Instead of crashing or forcing you to fill them in first, XGBoost's algorithm just automatically learns the best path for that missing data at each decision point. It turns a common data problem into part of the solution, which is incredibly efficient. So we have an algorithm that's smarter and faster, but what does that really mean in practice? Why should you, as a practitioner, actually care about this?
Well, this number says it all. In 2015, not long after it was released, XGBoost was used in 17 out of the 29 winning solutions on Kaggle, which is the premier platform for machine learning competitions. It wasn't just another tool, it was a dominant force that gave people a serious competitive edge. Even the creators themselves noted this. The fact that XGBoost became the go-to choice for the best data scientists in the world wasn't a coincidence.
It was proof that this combination of a powerful algorithm and a highly optimized system could solve a huge range of problems better than just about anything else at the time.
So, to put it all together in one sentence, gradient boosting builds a powerful predictor by creating a team of simple models that sequentially correct each other's mistakes.
And that leaves us with a final thought. What if the key to building truly intelligent systems isn't about creating a perfect model that avoids all errors from the start, but about designing a process that gets relentlessly better at finding and correcting its own mistakes?